can give it a next talk.
Alright. Hello everyone, my name is Ishika Agarwal. I'm a PhD student with Dr. Dilek Haqqani-Tour at UIUC. Today I'm going to be talking about our work called Cheap Neural Networks for Learnable and Scalable Influence Estimation of Instruction Fine-Tuning Data. So it's no secret that language model training fine-tuning is pretty expensive. For example, Meta came out with Llama 4 the other day, and the smallest model is just 109 billion parameters. It's also rumored to have been pre-trained on 32,000 H100s. I've also heard 100,000 H100s. Either way, it's way more than what we academics have. There's a third problem of scarce quality data. High quality data is very hard to obtain, it's very expensive. So there's a couple of solutions we can use for this. One, we can develop more efficient model architectures that don't use up a lot of space or they don't take up a lot of time. We can also design faster hardware that's easier to manufacture and is optimized for language model computations. Or we can use fewer data and learn as much information as we can from those fewer data samples. For the purpose of this presentation and my PhD work in general, we're going to be focusing on this third point here. So I mentioned the term influence estimation in the title. What is that? So influence estimation is a quantification of how important or how informative a data point is. If you've heard of influence functions from Ko and Liang back in 2017, or data evaluation, we're talking about the same thing. So in influence estimation, we have a data set. We're going to assign a number to every data point. Like, you are this important, you are that important. Then we can take the top K most important data samples and create a subset, and we can train our model on this subset. Now the goal of this subset is that the model trained on this subset should be as good as a model trained on the entire data set. So how is influence estimation usually done? Well, there are two broad categories. We have model-dependent and model-independent. For model-dependent metrics, we're trying to tailor this subset towards a model's capabilities, specifically its weaknesses. So the influence estimation there becomes how aligned is this one data point towards a model's weakness. And we can use model-specific signals for that, like performance, confidence, even magnitude of model gradients. On the other hand, we have model-independent. Here, we're more trying to solve how do we reduce the noise or redundancy within data itself. And so we can use clustering-based or semantic similarity-based methods for that. The more recent works in influence estimation calculate the influence of one dataset on another. So for example, the fine-tuning dataset on the pre-training, or a task-specific dataset on a general dataset. And what ends up happening is they kind of calculate this matrix of influence values, or matrix of similarity, or the similarity matrix, where each point in this matrix is the influence of one point on another. Okay, unfortunately, influence estimation is very expensive. It usually requires a forward or back propagation to a large language model. What's happening in this table is we see that these influence functions, they either have a really high cost or they use really, really large models with a lot of parameters. So one thing we notice is that these works, they estimate influence. You give it some text data and it outputs a numerical value. What if instead we learn to estimate influence? Wait, what does that mean? So on the left is the traditional, language model-based influence function. Again, you have some text data and you output a number. And there's a language model in between that does this kind of compression from text to numbers. On the right is what we are proposing. Instead of this language model, we use a neural network instead. Again, same input, same output, it's just we're using a neural network with way fewer parameters. So if we go back to this table, what ends up happening is that we still incur the same computational cost, but spoiler alert, the model size reduces by more than 99%. And this is what we call NN-SIFT. So NN-SIFT has three steps. We're going to first collect training data to train our neural network. Our neural network is called the influence network. So we're going to collect some training data for that. We're going to train the influence network, and then we'll evaluate it to get this big similarity matrix, the influence matrix we were just talking about. And then we can use that matrix for the downstream task of subset selection. So let's go over these steps. Okay, so first we're going to collect this training data. Like I said, we have this quadratic matrix of influence values. We're going to use an existing influence function to calculate just a small portion of those values. So this orange box here, we're going to just calculate just a few influence influence scores. And these are 4 of the influence functions we use. Now let's train our influence network with these few scores. So this is the exact definition in our code base. As you can see, it uses 2 linear layers, 1 Rayleigh layer in between, and we use mini-batch gradient descent to train this. So it's pretty straightforward. Now let's just take a step back really quickly and see, does this work? Okay, what's happening here is on the x-axis, we have the influence network training size. So yeah, basically how big is this orange box? Is it 1%, 5%, 10%, etc. On the y-axis, we have the mean squared error between the predicted influence from the influence network and the actual influence from the original influence function. And what we see from this graph is that with just 5% of data, we can achieve an MSE of 0.072. On the validation, what about the test? 0.063. Now, this is a really cool result to me, and I'll tell you why. So usually when you do influence estimation, you have a training set, you estimate your influence values, you do whatever you want with it, and then after that, you just kind of throw it away. You can't really reuse it anymore. If you need another training set, you have to do this all over again. But what this result shows is that we can use this same influence network model. We can use the same parameters for new data. So it's adaptive to new data. We don't have to just throw it away. This can be used for, continual learning or lifelong learning pipelines. That's what's really cool to me. Okay, so now with our influence network, we can fill in the rest of this similarity matrix or influence matrix, and then we can use this for, again, the downstream task of subset selection. So here's some results on that. Essentially what's happening here is we're using 2 datasets, mixed instruct and alpaca, and we're using the phi3 model. There's a lot of numbers on here, but what I want to show you is that the difference in performance between the influence function and the NN-SIFT variant. The difference in performance can be, positive difference or negative difference, but the average difference is just 1.4%. We also did this on llama, and here's 1.39. So essentially, this is pretty negligible. So essentially, NN-SIFT has absolutely no downstream task performance, no effect on downstream task performance. However, there is one effect, and that's in costs. Costs here, we calculate it with the amount of time it takes in seconds to run this algorithm. Costs are cut down significantly by at least 77%, up to 99%. Okay, let's take a step back. What does all this mean? So for NN-SIFT in this project, we found that influence estimation is incredibly expensive because it uses a language model. So we thought, okay, let's take out the language model, let's put a neural network in there. What exactly happened? We saw that with a neural network, we can learn it with very few data, it achieves a very low error rate, it scales with new data, it reduces costs significantly, and all of these benefits without a single drop in performance. So, thank you very much for your attention. This is our work. I have a poster at 1 p.m., number 7, so I'd be happy to take questions there, and also very happy to take questions down. Thank you. Yeah, go ahead.
So, thank you for the nice talk. A quick question for your model, how would you expect the generalizability to topics is never seen in the training data?
That's a good question. So if I understand it correctly, basically how does it do with out of distribution data, right? Yeah, that's a good question. I don't have results for that, but I assume that we'd probably have to retrain the model. However, because this is a neural network with 205,000 parameters, I don't think it's going to be a significant cost. But thank you for the question.
Thanks for the great talk. Does where you draw the box matter?
Ooh, that's a great question. You mean this little orange box here?
Yes.
Yeah, that's a great question. No, it doesn't. This is just, it's easier to visualize like this, so I drew it like this, but it doesn't matter. Great question. Okay, so now, yeah, go ahead.
Thanks for the great talk. I have a question related to your evaluation for your influence network. We truly see that the MSE mean squared error is kind of small, but I'm kind of curious, like what's the scale of these values? So if the values are all small, then maybe the small mean squared error doesn't mean you estimate the influence function well. And also if all of these kinds of like influence values are kind of like small, then maybe sometimes we care more about their ranking, not really about the absolute error. It's in many applications, I can imagine the absolute error would be not that important. We care more about the data valuation in their relative ordering. So do you have any insight or observation for that?
Yeah, that's a great question. The question was, what's the range of these values? So let me go back here really quickly. So for the first two and the last one, the score can be between -1 and 1, and then for the third one, it's usually 0 to 1. So it is a pretty small range. But I still think that because we're compressing from a very high dimensional space, from like text to a single scalar value, I still think that it would work for even larger ranges.
I see. Yeah. Thank you. I would be a little bit curious, like if we computed kind of like a Spearman correlation about the ordering, then what would happen? Yeah. But thanks for the
Yeah, no, I'll keep that in mind. Thank you very much.
Yeah.
Okay, thank you. Oh, yes.
I wanted to ask about the actual data that you saw that was influential. Were there any particular insights you got from applying this influence network on what data is influential?
Yeah, that's a great question. So usually when data is influential, it means that it's pretty different from the rest of the data, or at least, for example, when I was talking about the model-independent methods, usually what ends up happening is if you cluster all your data, you choose all the centroids, then those data are most different from each other. So that's pretty much what influence estimation does as well. It chooses diverse data that is also representative of the entire data set. That usually generally happens for model independent and dependent.
Okay, thank you.
Thank you for the question. Okay, thank you.